Hello everyone, in this video I'm going to be talking about the effects and the equations of adding a non-volatile salt. This is going to be the last video for the whole semester, so yay. I don't know, maybe we'll continue to make videos like this, but they'll be like higher level chemistry classes if I do decide to make them, but likely not, just because I'll be a busy bee in the next few semesters. But if anybody of y'all have been watching all of the videos, I do appreciate it. I hear from some classmates, they're like, it's really helpful just to get a little bit of a rundown and do some practice problems and see somebody else do it. But yeah, I'm sure people are watching these videos that aren't even in my class and are just looking them up on YouTube and they just happen to pop up. But yeah, so this will be the last of all the videos for this semester, so let's get into it. Alrighty, so again, we're talking about the effects and the equations of adding a non-volatile salt. So, what a non-volatile salt is it's a salt that isn't easily, it doesn't evaporate easily, right? Or it doesn't evaporate at all. So, have you ever seen this, I don't know, if you've ever done an experiment where you have salt water, you boil off the water, the salt stays in the bottom of your, what do you want to call it, pot. Same thing with sugar. If you have sugar water, you evaporate off all of the water, you're going to have sugar at the bottom. So they don't evaporate. They don't, evaporate when you heat it up, right? So it's a non-volatile salt, which the most common ones, as we've talked about in class, are going to be sucrose and your salts. So NaCl is a salt. Anything that is a non-metal and a metal is going to be your salts. But yeah, so the addition of a non-volatile salt to a solvent affects the vapor pressure, the boiling point, and the freezing point. So similar to the things that we've been talking about, basically just all of the colligative properties, vapor pressure, boiling point, freezing point, those are the things that we're going to have to work with here. The solvent for our class is always going to be water. You can do examples where you're using ethanol, but just to keep things simple, Professor Sherlock has made it just water. And it's also the most likely one that we're going to see, right? We're not usually using any other solvents in our Gen Chem labs. We're usually just using water. All right, so let's talk about the effects. So generally when a non-volatile salt is added, the vapor pressure goes down, the boiling point goes up, and the freezing point goes down. So I have a little picture here. So this is water. Water has a freezing point of 0 degrees Celsius, which is something that you're going to need to know. So make sure that you are keeping that in your mind. Apologies for my dog barking in the background. So yeah, water has a freezing point of 0 and has a boiling point of 100 degrees. Using this little line graph chart here, dot plot, whatever you want to call it, anything that's below the freezing point is going to be a solid, anything between the freezing point and the boiling point is going to be liquid, and anything above the boiling point in degrees is going to be a gas. When we're adding the non-volatile salt, what we see here is a little shift, right? So the freezing point actually shifts to the left, so it's becoming more negative, and then the boiling point goes up, so it's becoming more positive. So the freezing point decreases, and the boiling point increases. Vapor pressure kind of just goes along with the boiling point. So because the boiling point goes up, that means that it's harder, or it takes more energy for it to be turned into a gas, right? Which makes the vapor pressure go down because it's less likely that there's vapor coming off of the liquid. But yeah, so we can see here that it shifts over, and then both of them shift over. So you're actually increasing the amount of temperature that the liquid is able to stay a liquid, right? It takes a lot more energy to become a gas, and it takes a little bit less energy, or more of a, I don't know, yeah, just less energy to freeze into a solid. So that's one way of thinking about it. But those are the trends that you'll have to know. Okay. Let's now talk about, not this one, let's talk about the equations that we're going to be looking at. So same thing, we're using vapor pressure, freezing point, and boiling point. One thing to note about the freezing point and boiling point ones is that they are the change in the freezing point and the boiling point. So this just gives us the amount that something changes. So let's say that something goes from like 100 degrees Celsius, which is what we're going to be dealing with, to maybe 105 degrees Celsius. So we're going to do our final minus initial, and we're going to get 5 degrees Celsius change. So that's all that that's telling us. It's just telling us to the degree how much did that change, right? So with vapor pressure, the equation that we're going to use is PA is equal to XA and then PA naught. So what all this means is P is the vapor pressure. So P just means vapor pressure. I actually like to write mine as VPA is equal to XA and then VPA naught. Just because that helps me to know, like, okay, that's vapor pressure. I'm not going to mess that up. But yeah, you can write it however you'd like to, but as long as the math is the same. So P is the vapor pressure, A is the solvent or liquid, so this is the vapor pressure of, we're going to be using water, so water, the mole fraction of water is X, so we're using those mole fractions that we did a little while ago. And then PA naught is going to be the initial vapor pressure. He writes it like this, and so does the textbook with the 0 at the top. I like to write my naughts at the bottom. Basically, all that naught is, it's a Greek letter. You could say it's 0 also. It's just telling you that that's the initial. So that's where you start. So let's say that you're being told that the vapor pressure is, I don't know, like 300 millimeters of mercury. You then multiply that by the mole fraction, and then that's your final vapor pressure. Okay, the next thing to look at is freezing point. So freezing point, again, is the change in freezing point. So the change in freezing point is the molal, so not mass. Keep that in mind. This is molal. Molal, not mass. You might see that and be like, oh, that's mass. No, it's molal. And then Kf is your freezing point depression constant. And then I'm going to be talking about a little bit later, but it's basically the amount of ions or molecules that will dissociate per molecule. It's similar to moles. It's just telling you, okay, this is how much you're going to get out of it once it dissociates. All right, and then change in boiling point, very similar story, but we're now working with the boiling point elevation constant. As we know, the boiling point goes up and the freezing point goes down, so that's why they're called that. And again, it's just the change in boiling point. So with I, let's talk about I for a little bit. I tells us the amount of ions or molecules that will dissociate per original molecule. So for sugars or alcohols, it's going to be os or all is going to be the ending. So we have something like ethanol, alcohol, isopropyl alcohol. It's bad that I can't think of anything else. Phenol is one, that's an alcohol. And then you have your oses, your fructose, your lactose, your glucose, your sucrose, things like that. Those are your sugars and alcohols, and those are always going to be equal to 1. So as soon as you see OL or os at the end, all or os, you know your I is going to be 1. The reason why it's 1 is because if you have something that's nonpolar, well, it's not technically nonpolar. I guess you could say that they're covalently bonded. It's not a salt. Anything that's not a salt is going to only break down into its separate molecules, right? So let's say that we have something like, this is usually a liquid, but let's just say, for instance, that this is a solid, right? And we're melting them together, or not melting them. We are putting it into water and dissociating it. So between all of these molecules within a, let's say a chunk of salt of this, CHH, they're actually bonded like that. So those are like your intermolecular forces. And the only thing that you're doing when you are adding something, let's say this is a sugar, like a shorthand for sugar, all you're doing is you're breaking that intermolecular bond. You're not breaking any bonds between these guys. The intermolecular forces are just breaking. And then we can look at how our salts are a little bit different from that. So that has to do, so this is all your oses and alls. All you're doing is breaking the intermolecular forces. So I'll say that breaking, I'm just going to say intermolecular forces. So for salts, it's a little bit different. I is going to be the amount of ions present once dissociated. So there's no ions associated, there's just molecules that are dissociating, but this is the ions present, right? So when we have NaCl and we add that to water, what's actually happening is you are going to create ions. So here we can count the number of ions that are formed, right? So we have one ion and another ion, so that's going to be 2. So the I factor for that is going to be 2. Now let's look at, let's think of another one, CaCl2. When we dissociate that, we're going to get Ca plus 2, and then 2Cl minus. So 1 plus 2, the I is going to be equal to 3. Now some of the tougher ones are going to be with your polyatomic ions, right? So when you see something like CaNO3 or H2SO4, things like that, these are your polyatomic ions. And you can look up, actually, common polyatomic ions. And there's like lists of them, right? Your acetate, ammonium, carbonate, chlorite. Those are ones that you're going to commonly see. It's important that you keep an eye out for those, and you don't have to memorize the charges or anything. You just have to memorize that they exist and when to know how to spot them. Really, the main thing with how to spot them, which one do I want to be on? Oh my gosh, there's too many tabs. Okay, it's finals week, guys. So the main thing you want to really look out for is there one metal, right? So it's always going to be a metal plus a non-metal. So if you have one metal, the rest of it is your non-metal, right? So let's say you have, let's say you have NO3. You could say, okay, well that's my metal, so this has to be all one thing. So this is just 1. So then this I would be equal to 1, if that makes sense. So yeah, once you have your metal established, like sodium is my metal, the rest of it is going to be an ion, or a non-metal, which will dissociate into one ion itself. But yeah, so that kind of explains the I thing. Another easy way to do it is just count the subscripts. So for instance, with this one, you would just count 1 plus 1 is equal to 2. CaCl2, you could just say 1 plus 2 is equal to 3. Or you could break it down into the ions and count them that way. You're both basically doing the same thing there. Okay, so let's get into some practice problems. So the first one is a vapor pressure practice problem. So it says that the vapor pressure of pure water is, all right, so I'm going to put this, pressure is equal to, we're using water, so let me write that down as water. Pressure of H2O is equal to 23.8 torr. What is the vapor pressure of a solution made by dissolving 18 grams of glucose in 95 grams of H2O? All right, so the thing that we have to look for here is really just our mole fraction. So we have to find the moles of both of these. So let's do 18 grams of glucose. I'm going to say GG, grams of glucose. And we're just going to do our little mole conversion. 1 mole, 180 grams of G. And that's going to be, I think it's just 0.1, but it doesn't hurt to check. 18 divided by 180. Yep, 0.1 moles of glucose. And then the 95 grams of water. So we have 95 grams of H2O divided by 1. And the molecular weight for water is 18 grams per mole. You can calculate that. I just have that memorized. It's just 2 hydrogens with a weight or a mass of 1 gram per mole. So 1 times 2 is 2, plus 16 is 18, because 16 grams per mole in an oxygen. So, yeah. So we have grams of H2O, 1 mole. Alrighty. so that's going to be 95 divided by 18, and we get 5.2, I'm just going to round it to 8 moles of H2O. Okay, so now, the mole fraction, if we remember from the other videos, is going to be the moles of whatever the mole fraction you're looking of. So we're doing H2O, so it's going to be moles of H2O plus the total moles. So it's going to be moles of H2O plus the moles of the glucose. So this is going to equal, so the H2O is 5.28 moles. And then we're going to do 5.28 plus 0.1 mole. Alright, and then we do that on our calculator. It'll be 5.28 divided by 5.38. 5.28 divided by 5.38, and we will get 0.98. We'll say 981. Alright, now what we're going to do is we're going to add that into our equation. So we have PH2O is equal to XH2O, which we just found, and then the PA, or PH2O, not. This is actually the not one. Alright, so the PH2O, so the new pressure of the water is going to be 0.981, and then the pressure in the beginning is 23.8 torr. So once you multiply that times 23.8, we'll get a pressure of 23.4 torr. It's really 23.357, but I just rounded up, and let's see what he got, 23.2. Cool. So that would be your answer for that, and that would be the process as well. You don't have to convert the pressure because the question has it in torr, and it's not specifically asking for it in millimeters of Hg, which would be the same, but it's not asking for it in atmospheres or anything. So you can just give it in whatever answer. But if you see on your test, let's say the test is like blah, 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 ATM, or blah, 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 ATM, or blah, 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 ATM. You're like, oh crap, why are all my answers in torr, but the questions here say ATM? All you have to do is just convert it. So although they may not explicitly say convert it, sometimes there's a situation where you're like, uh-oh, all the answers are in atmospheres, I guess I should convert it, right? So you may come across something like that. He usually doesn't do that on the test, but it's always something to keep an eye out for. Not to panic and just convert when you need to. Alrighty, the last question that I'm going to go over is a question on the change in freezing point and the change in boiling point. So this is our equation here, but we are going to be dissolving 396 grams of sucrose in 624 grams of water. We're going to calculate the new boiling point and the final boiling point, or not boiling point, the new boiling point and the new freezing point after the sucrose is added. Okay, so the first thing I'm going to do is actually find the molal. I'm going to actually give you these values as well here. KB, just look it up, KF of H2O. Oops, that's not what I want. Oh, that's a scooter apparently. Fancy. KF of H2O. Okay, 1.86. 1.86. I'm pretty sure this is 0.52, but let's just check it. This will all be right on the test. You don't have to memorize this. Okay. 0.512. Okay. Cool. Alrighty, so let's first find the molal of this. So in order to do molal, it's another thing that we'll have to know is it is the, pretty sure it's the moles of the solvent divided by liters of the what is it? I'm gonna check back in my notes. This is something I'm actually gonna put on my note card because I'm like, it's a new thing for me. I've never learned it before and I always forget it because I get it mixed up. Okay, so moles of the solute. Sorry about that. Moles of the solute divided by moles, or not moles, sorry. Liter or kilogram solvent. There it is, kilograms solvent. Oh my goodness, that was rough. Okay, now that we have that information, we're gonna calculate the molal of this new mixture. Okay, so the first thing that we actually need to do is find the moles of the solute. So keep in mind the solvent is the thing that's dissolving. The solute is the thing that is being dissolved. So we're going to find the moles of our sucrose here, given this information. Okay, so we have 396 grams of sucrose times the molecular weight, which is 1 mole, 342 grams of sucrose. Do that out in your calculator. You're going to get 396 divided by 342, which will be equal to 1.16 moles of sucrose. And then we're going to convert this into kilograms. So the water is 624 grams of H2O. Converting that to kilograms, there is in 1 kilogram, there's 1,000 grams. So this is going to be 0.624 kilograms. All right, finally on to molal. We can do the moles of the solute, 1.16 moles divided by the kilograms of solvent, 0.624 kilograms. Okay, so 1.16 divided by 0.624, and we should get 1.86 molal. Just check my work here, make sure that that's all right, because I know it, apologies for my dog, I know I make a lot of calculation mistakes sometimes because I'm not too good at the calculator. I'm fine with doing calculus, which is the weird thing, but as soon as somebody's like, what's 4 times like 8, I'm like, I don't know. It's a darn good question. I don't even know it. Is it 32? 4 times 8? Okay, it's 32. I know my times tables, I guess, sometimes. Alright, anyways. So first let's calculate the freezing point, right? And I feel like doing that one first. The changing freezing point is going to be the molal, Kf, and then I. Alright, let's determine what I is too. So I is going to be the amount of ions that dissociate. This is a sugar, so that means that the I is going to be equal to 1. So it ends in ose. That's our ending there. So we're like, awesome, ose. That ends in, you know, what we need to for it to be equal to 1, so that's just going to be 1. So I'm going to say freezing point is equal to the molal, which is 1.86 molal. And then the Kf is 1.86. Interesting. I think we went over that in class about how funny that is. 1.86 times 1.86, and we will get a change in freezing point of 3.46 degrees Celsius. Now, it's asking for us to find the new freezing point. So what we're going to do is, because the freezing point of water, so the initial freezing point initial, is going to be 0 degrees. We know that when we add a non-volatile solvent, or a non-volatile salt, salt, solute, what's going to happen is that the freezing point is going to lower. So this is just telling us how much it changes by. So that's just the magnitude. We need to know how, which direction. Is it moving positive or negative? So it's actually going to move it to the negative, right? So if we think about it again like a line, here's our starting point. It's going to go lower. It's going to be going more negative. So that means that the final freezing point is going to be negative 3.46 degrees Celsius, because the freezing point goes down as you add a non-volatile salt. All right, now that we have that one done, we can do the change in boiling point. and it's going to be mkb I. Again, I is going to be the same thing, so we can just say that we're doing 1.86 molal times the 0.512, and then times 1. You don't have to add the 1 in there, but I'll just show that there. And then we have the boiling point is going, or change in boiling point is going to be equal to 1.86 times 0.512. So this will be 0.95, we'll just say 0.95, right? No, we'll say 0.952. Get it to 3 sig figs. Degrees Celsius. Now, again, thinking about that number. The original boiling point of water, this is something that you just have to know, is 100 degrees Celsius. We know, let's say this is 100 degrees, we know that when we add a non-volatile salt, it's going to go this way. So we're increasing the boiling point. So we're going to add this to 100, and we're just going to get 100.952 degrees Celsius. And that would be our answer for our boiling point. Put that in there. Alrighty, so that is all that I have for this video. Again, keep in mind, he's going to give us those KF and KB values. Not something that we have to memorize, but what you do want to memorize is the freezing point and boiling point of water. Remember what molal is. I know he's going to give us a sheet. I'm going to actually look right now, see exactly what's going to be on there. So we can see if that's something that we need to... I'm totally in the wrong sheet right now, aren't I? Yes, I am. Took me that long to figure it out. Unit 4. Do I not know where the notes are? Oops. Is this it? There we go. Okay, well, if you tilt your head, we are actually going to be given the moles, the molality. So we're going to be given that. So these are the things that you're going to be given. I highly recommend making a note card, including the things that aren't on here that you want to know for the test. But yeah, good luck to everyone on your finals. Thank you all for watching these videos. I do appreciate the view count. No, I'm just kidding. My main goal was to really help people. I do enjoy this subject, and I'm trying to get better with like the way I explain things and the way I teach things. So I figured that making some videos would help me and also help my classmates. So thank you all for watching. Again, I appreciate it, and feel free to reach out with any questions. Good luck to all. Thank you.